Hello again. This tutorial on resistor capacitor circuits picks up where the last one left off. So if you're not familiar with the circuit that you see in front of you, then I suggest you go back and watch the last tutorial in the series. I had the same circuit, albeit without this extra loop on the right hand side that I've got. I've got the same capacitor, 0.1 farads. I've got my 25 ohm resistor. I've gone back to having 5 ohms internally in the battery, which is how I started off with the last example. I've got a 120 volt battery, and as I said, this time I just have one extra path in parallel across the capacitor, and there's a 10 ohm resistor over there, and then I've got a separate switch for that branch of the circuit, which again currently is open. And I'm going to play with these switches and close them and look at the currents and the voltages across different elements at different times and see how this behaves. And again, I strongly urge you to go back and watch the first video in this series just so you can appreciate a little more what's going on. For example, I'll talk a bit about the RC time constant for the circuit, which I explained last time. So it's important that you know that going into this here. All right, I'm going to start off by closing the switch up here, and I want you to watch the behavior of this circuit. This one will remain open, but this one will close. Here we go. Okay. All right, there it is. The capacitor is currently in the charging stage. The current, which began at 4 amps, is exponentially decaying and asymptotically approaching 0. And that's that. As you can see, nothing has happened in this branch of the circuit. There's been no movement of these negative blue charge carriers that we see in the wire at all during the time that I had that switch closed. Okay, I'll reopen it, and I can reopen it and close it as many times as I want, but that capacitor is going to remain charged. So at this point, nothing else can happen unless I turn up the voltage of the battery or turn down the voltage of the battery. Right? Then we might see some more transient behavior, but at least for the time being, nothing else happens. Okay, what I'd really love to be able to show you is this stopwatch. I'd like to actually be able to discharge the capacitor like that, right? And I'd love to be able to close the switch at time 0 and start, but unfortunately I can't get my mouse over quick enough. So what I'm going to try to do is I'm going to start the stopwatch, and when it gets to 2 seconds, or maybe we'll wait till 10. I have a nice easier number. I'm going to shut this switch at exactly 10 seconds, and so then we'll just assume that's 0, time 0. And I want you to watch what happens, because in this particular circuit, the RC constant, product of R and C, is 3, right? Because I've got 30 ohms of resistance total, 5 here, 25 here, and I've got 0.1 farads of capacitance. If you multiply those together, you get 3 seconds. And it turns out that that time is the amount of time it takes for the current to decay to about 37% of its initial value. 37% of its initial value. And that time in this circuit is 3 seconds. So if the initial value of the current is 4 amps, then after 3 seconds, which for us will really be 13 seconds on this clock, we should see the current down to about 37% of 4, which is about 1.5. Okay, let's see if that happens. Here we go. 5 seconds to go. I realized I could have done this at any time. Here we go. Boom. Okay. Watch it. Watch 13 and watch this current. Here comes 12, 13 now. 1.5 amps. We saw right there. Right? If you didn't get that, you can go back and replay the video as many times as you want and pause it. And you'll see that at time 13 seconds, 3 seconds into the transient phase of this current flow, we were at about 37% of 4 amps. Cool. Also, that constant, that time constant, is the amount of time it takes to get to about 68% charge, final charge on the capacitor. 68% of the capacitor's final charge. Right, we could have also watched that, although we can't measure the charge directly across the capacitor. We can always put the voltmeter there. Right? And we can calculate using Q equals CV to get the final to get the charge on the capacitor at any moment in time by measuring the voltage across it. And as I had on this whiteboard from the last video, I did that actually. We found out that the final charge on this capacitor was 12. So what we also would have seen is that 3 seconds into the circuit, we would have seen that the charge on the capacitor at that moment in time was 68% of 12, whatever that is. All right? Okay, so I'm going to go back to the circuit here. I'm going to discharge my capacitor. Okay, let me open the switch first. Right? Discharge it. Right now, I'm going to play with the other switch, and we're going to both charge the capacitor and then discharge the capacitor the real way, without me having to click here and say discharge. Okay, and I want you to watch the behavior to see what goes on. It's all very, very intuitive. So here goes. The switch is closed. Okay, the capacitor is charging. Again, nothing happening here. This is an open branch of the circuit right here. There's nothing happening. It's charging, it's charging. By the way, that's not to imply that there's no potential difference across here. There is a potential difference across that switch. It happens to mirror the potential difference across the capacitor. That's interesting, right? If you ask yourself why that is, I think you'll convince yourself very quickly. If you think about Kirchhoff's loop rule, you'll realize why in this loop here, the voltage across this capacitor, this switch, must mirror the voltage across that capacitor, because there is no voltage drop across this resistor, right? So there is a potential difference there, but there's no current flowing anywhere in that branch of that circuit, at least not yet. All right, so I'm satisfied. 119.996 is the voltage across either the switch or the capacitor. Let's leave you there. All right. So I'm satisfied. It's fully charged. As much as we're going to see, the current has decayed to essentially 0. And now I'm going to open the switch. Okay, and the capacitor remains in this fully charged state with no way for these negative charges on this plate to get back around to this positive plate and neutralize, right? Or in the language of conventional current flow, we would say there's no way for these positive charges to get back around to the negative plate to neutralize. But there is a way, isn't there, right? Because now I can close this switch, and I can take this infinite ohms of resistance across an empty switch, and I can remove it. I can lower it to 0 ohms in a perfect switch. And when I do that, what I now have is a circuit consisting of just this capacitor and just this resistor. The battery is out of the picture. This resistor over here, 25 ohms, 5 ohms, all out of the picture. This now becomes my loop. And you're going to see current flow in this path here, although you're going to see electron flow. It's going to go counterclockwise from the moment that I close the switch. And it's going to start off high. The current will be very high in the beginning, and then it will decay to 0. And I think I can show that. I'll just put the ammeter over here, right, just so you can actually see the reading as time goes on. Ready? Here we go. Watch that capacitor discharge. All right. And again, no action over here on the left branch of the circuit and that loop. It's all over here. Its capacitor is now discharged. That's a more realistic discharging of the capacitor. And again, it doesn't happen instantly. And that's the point that I want to stress here. Nothing with capacitors is instantaneous. It takes time to charge them. It takes time to discharge them. So clicking here and saying discharge capacitor is unrealistic. You have to discharge it through something, and that something is always going to have a little bit of resistance. And the product of that C and that R is going to give you the new time constant for the decaying of the current across this circuit right here. In this case, the time constant is 1 second, because I have an R of 10 and a C of 0.1, and you multiply them. Get your 1 second time constant. All right, not only that, but if we open up the switch and charge the capacitor again, give it a moment to get back up to full potential and charge, I want you to watch the value of the current in this loop of the circuit. I want you to notice initially what it is, and I want you to notice how it decays to 0 as time goes on. I start off with a voltage across the capacitor of 120, and I only have a resistance of 10. All right, good enough. We'll stop it there. So that means I should see initially a current of 12 amps. Let's see. Yep, I think I do. All right, again, if you don't believe me, you can go back and rewind the video and watch. But it starts off in the high 11s. And I can actually stop the discharging and just continue to open and close the switch. It gets back down to 0 amps, though, relatively quickly, because there's only 10 ohms of resistance in this path. It takes much longer to charge the capacitor. I don't want you to see that yet. let's open this switch. It takes much longer to charge the capacitor than it does to discharge it. And that's because I have more resistance in this loop than I do in this loop. It discharges very quickly. Okay, discharging capacitors also follow exponentially decaying current versus time functions. However, the charge on them and the voltage across them is also decaying. It's not increasing. When you charge a capacitor, the voltage across it and the current rise. When you discharge a capacitor, the voltage across it and the current and the charge on it drop. All right, but what I'm really interested in doing is, the real point behind this is, I just want to leave this switch closed. Okay, I want to leave this switch closed and let this be a parallel circuit to begin with, where I have a resistor in parallel with a capacitor. And then I'm going to close this switch. And I want you to watch what happens. I'm going to take and maybe put, I think I can only unfortunately have one ammeter at a time. So I'm going to put my ammeter here. Okay, and I'll leave my voltmeter, I think, right where it is. Okay, so just sit back and watch the behavior of this circuit. Now, actually, before I do, it might be a good time to pause the video and ask yourself, do you know what's going to happen when I close the circuit? Do you know when I first close the switch where the current will go? Which of these branches will see more current initially, which will see less? And then what will happen over time as time approaches infinity? Will things change? Right? So if you want to give yourself a minute to think about that, pause the video and come back. Right? And then we'll start here. Ready, go. And that's it. We've reached a steady state at this point in time. Now there's only a 30 volt potential difference across the capacitor, not the 120 that you had before. And that's as high as it's going to get. Current seems to be flowing continuously and steady in the outer loop. And watch what happens when I open. Now there's a discharging going on. All right, we're back to where we started from. Once again, watch that one more time. Here we go. Notice that the current initially follows this path through the capacitor. None here in the rightmost branch, although it changes very quickly. See that? And then as time goes on, this becomes the branch that's traversed by current continuously, and this one plugs up and stops. And the whole circuit eventually reaches a steady state where it's as if the capacitor is sort of not even here at this point in time. You can see you have 3 amps of current continuous, which makes perfect sense, right? Because you've got a battery that's 120 volts, you've got 5 ohms of resistance, 25 ohms of resistance, and 10 ohms of resistance. Add that all up, you get 40 ohms. 40 ohms, 120 volts, 40 ohms, that's 3 amps, according to Ohm's law, and there you see it, 3 amps. And it will continue like this indefinitely, on and on and on and on, while this branch of the circuit is simply plugged up, right? And then when I open, this charged capacitor can now discharge along this path. See that when I first close the switch, look at the current on the ammeter. When I first close it, it's 4 amps. Right? And it's 4 amps because all the current was actually traveling through down this branch of the circuit, up to the capacitor and then leaving on the other side. There was initially no current in this branch of the circuit because without any resistance in the capacitor path, all of the current chose that path. Effectively, we shorted out this resistor here, at least just initially for that brief instant in time. All right, and now we reach our steady state. So it's really important to understand as time goes by how things trade back and forth inside this circuit. What exactly is going on? So I'm going to actually come back to my my diagram, my whiteboard. I'm going to draw this, and let me open up this circuit here. All right, and I'm actually going to reload it, and hopefully that'll allow my fan to quiet down. All right, so this is the circuit that I had before from the last video tutorial, and I'm just going to erase what I have here a little bit. Okay, and we'll go back and we'll look at this now in light of the new scenario, which is to put a second resistor in series, or in parallel, sorry, with the capacitor. So that looks like this. So we'll come over here and let's put this resistor, I'm just going to draw it way over here so we have room, like so. And I don't need to have my switch there because I'm just going to leave it closed as it was. And this is 10, this is R equals 10 ohms. All right, so let's ask all the standard questions, such as what happens at t equal 0? At time 0, what are the values of the current in each resistor, let's say? And what is the value of the potential drop across the different resistors? And the capacitor, for that matter. Right? Let's call this R1, and let's call this R2, so that we can refer to these things. Right? So at t equals 0, what's going on? I'm going to look at I. I'm going to look at the voltage drop, delta V, across resistor 1. I'm going to look at the voltage drop across resistor 2, and I'm going to look at the voltage drop across the capacitor. Again, all at time t equals 0. Right? What are they? And we can figure this out intuitively and conceptually without any knowledge of the calculus that's behind all of this. As long as we think about Kirchhoff's loop rule and these two equations up here, we've got we've got everything that we need. So let's start off with the current, all right, at time 0. So we already know the answer to this question from before. When the switch is first closed, this path between here and here is a resistance-free path. There's no R anywhere in that wire if it's a perfect wire. So it's effectively behaving like a short circuit around this path here. No current would dare flow down this path. Why? When there's a resistance-free path this way. So all of the current will take this direction. I'm now going to draw an arrow in the direction of positive conventional current flow, like so, right? Opposite with from what PHET is showing us. So with all current following this path, and again, it's important to stress that no charges actually flow across the capacitor. They go up to it, they leave the other side. The only thing that's really in between those plates is the electric field itself, which is not physical charge manifestation. It's not a flowing of charges. Okay, so charges go up to and then repel from the other side. Top plate becomes positive, the bottom plate becomes negative as time goes on. And so initially, the only resistance in this circuit is the 30 ohms that I have. Now really what I have is I really have 25 ohms up here, don't I? Right? The 25 ohms followed by the 5, there's a little 5 ohm internal resistance inside here. Right? So it's really that, but that's 30 no matter how you look at it, okay? So in that instance, I wind up with an initial current of 120 volts for my battery divided by 30 ohms, like so, and that gives me 4 amps, where I've left off the units in my calculation, sorry. Just as we would expect. What's the voltage drop across our resistor R1? At that moment in time, and I wonder, should we go back just to make things simple? I know I keep jumping back and forth with these internal resistors. Maybe it would be better if we, well, you know what? No, let's leave it alone. Let's leave it alone. Let's add in an additional resistor. Let's call this V, or let's call this R for internal. Let's call it RB for resistance of the battery. R sub B. All right, and we'll just put that right down here like this. VB. Like that. Okay. So let's see what these all say. So I've got a current that I've established of 4 amps. So that tells me that at this resistor right here, R1, I've got 4 amps, 25 ohms. That gives me 100 volt, just multiplying them together, right? IR. That gives me a 100 volt drop across that resistor. And then looking at this VB down here, again, I've got 4 amps and 5 ohms. That's a 20 volt drop. There's my 120 volts. As per Kirchhoff's loop rule, there is nothing left. There's no voltage lost across here. So this is a 0 volt. Delta V C is reading 0 volts. And also this is 0 volts. And you know what? These two, this one and this one, have to always show the exact same potential difference across them. They can't ever differ from each other at any instant, because this itself, this path that you see right here, we could actually talk about this as being a loop, a Kirchhoff's loop, and we would have to see the sum of the voltage rises and drops around this loop would also have to be 0. So whatever voltage rise we see here, we have to see dropped over here as well. So these will always mirror each other exactly in terms of potential difference. So 0 and 0. All right, that's what happens initially. Now, as time goes on, after a long time, let's say, in other words, when the circuit reaches a steady state, this is after several time constants, factors of RC have passed. So we'll say as t approaches infinity, like that, what are the answers to all of these questions right here? What ends up happening? Okay, and I think rather than just redrawing everything, I'm just going to put some lines over here. We'll just go like this. We'll go like this. Like this. And like this, right? And we'll just fill in all those values again after a long time. So after this time has passed, the capacitor is essentially a roadblock. It's completely filled, right? No more charge can pass into it or leave it unless you were to turn up the voltage of the battery, that is. So if that's the case, this becomes a dead branch of the circuit in the sense that nothing can flow. So all the current will now be flowing in this outside loop. Right, so whereas I had no current flowing through resistor R2 initially, I now have all the current flowing through resistor R2. And so this path out here is looking like just one big series path with resistance. I have 10 ohms, 25 ohms, 5 ohms. That gives me a total of 40 ohms of resistance around this outer path. With a 120 volt battery, it's not hard to see that's going to give me a current of 120 over 40, which is 3 amps. This is the exact behavior you saw modeled in that little PHET circuit. All right, as time went on, the current here from the battery approached 3 amps. It started at 4 and it dropped to 3, and it's going to stay there at 3. Now the voltages across the different resistors look like this. Let's do R1 first. So that's 25 ohms, and what's the current? 3 amps through it. So multiplying V equals IR, that gives me 75 volts of potential difference across that one right there. Let's do this one right here. Again, 3 amps. 3 times 5 is 15. Gives me 15 volts of potential difference across that resistor. All right, 75 and 15. I'm already up to 90 volts. I'm missing, how many volts am I missing? 57. I'm missing 90 volts. I'm missing 30 volts. Right, because I've got a 120 volt battery and I'm at 90 volts. I'm missing 30 volts. Where is that 30 volts being dropped? Actually, I made a mistake. Forgive me. Ugh. That's the wrong place to put that. I wrote the answer in the wrong place. So actually, it's down here. This is 15 volts right there. That's the 15. Okay, still, I'm up to 90 volts, and I'm missing 30 volts. That missing 30 volts is being dropped across resistor R2 right there. 30 volts. Now, if you don't believe me, well, you could just Ohm's law again. V equals IR. You know that the current is 3, and you know that the resistance is 10, and there's your 30. Okay, again, Kirchhoff's loop rule. Check. Everything here adds to 120 volts to match the battery. Here, voltage across the capacitor. Well, remember I said anything in parallel with anything else, if they're the only two things in parallel with each other, they must have the same voltage across them. It's another way of simply saying, in a loop that you were to draw around this path here, the voltage rise and the voltage drop across these elements would have to sum to 0. So that means whatever the voltage difference is across this resistor, it must be identical across this capacitor. So by finding that the voltage is first 30 volts across resistor R2, I now know that the final voltage across the capacitor must also be 30. There's no other option. Okay. With that information, I can now go ahead and calculate, if I want to, the final charge on this capacitor. Q equals CV. Using this equation, I have a capacitance of 0.1. I have a voltage difference of 30 volts across it. And now I have a charge of 3 coulombs, which is a lot of charge, stored on that capacitor. Okay. Previously, in the last example, when the voltage across the capacitor, this is the last video, the voltage was able to get all the way up to 120 volts, I was able to store much more charge, right? I had 12 coulombs, I believe, across the capacitor. But now, since the voltage across this capacitor will never rise to be greater than 30 volts, because it's in parallel across this resistor right here, which is at 30 volts, this capacitor will only achieve a final charge of 3 volts. Okay, and this, by the way, was all done with this switch closed. I forgot to draw the closed switch in the beginning. But if I reopen the switch, now I have a very different circuit, right? Because now I have a circuit. So let's go kind of to this and say, okay, the switch is reopened. And I just want to reset and call this one more time equals 0. I realize that we just let time go to infinity. We're going to reset and say, now this is time 0. So effectively what happens? What are the readings across these things? And there's only 2 things to look at this point. There's V sub C, and there's V sub 2. Right? And I guess there's also the current I. We could also say, what is that at those different times? Okay, so initially when I first open the switch. So let's see how this goes. So voltage across the capacitor, we know from a moment ago that that was 30 volts. Right? It's going to be 30 volts still because there's 3 coulombs on that capacitor. With 3 coulombs, right, here, and a capacitance of 0.1, there must, again, instantaneously still be 30 volts across that capacitor at the moment that we open up this big switch over here. All right? Well, that means with this resistor right here facing a 30 volt potential difference, this resistor also has 30 volts across it. That means the current in that resistor right there is what it was a moment ago. 3. 3 amps, correct. Right? Because the resistance is 10 ohms and there's 30 volts across it. That's initially. Now, as time approaches infinity, clearly things change. We know the current is going to approach 0. Right? We know that as this capacitor eventually discharges. And we also know that the voltage across the capacitor is going to approach 0 because there'll be no more charge left on it. And we also know that the voltage across the resistor is going to approach 0 because there'll be no more current through it, because I is 0. And everything will decay to 0 as time goes on. But at least initially, when we first reopen this switch, this is the behavior that we see at that moment in time. We see basically a continuation of what we saw over here. The capacitor almost acts as sort of like a battery for a little bit, but it can't keep up, right? There's not a continued source of energy inside that battery. All there is some stored charge and some amount of energy that we can calculate that's equal to 1/2 CV squared, the energy stored in the capacitor. And that's going to dissipate as time goes on. That energy is going to be used to actually pump the charge through that resistor, dissipating it as I squared R, right? Or the heat dissipated in that resistor. And as time goes on, that capacitor will just sort of lay down and die, give up. It's not like a battery where there's a continued source of energy owing to a chemical reaction of some time that has a lifespan that's of some significance. All right, and that's how this circuit is going to behave. We can get a lot of information and understand quite a bit about the behavior of these circuits without actually having to do any fancy mathematics. Now, of course, to really get a sense for what's happening at any time, like to be able to say what is the current in the circuit in any particular place at time 2.5 seconds after the switch is closed, or what is the voltage drop across resistor R1 at time 3.8 seconds after the switch is closed. To get those exact actual values, we need to do some math. We need to specifically solve a differential equation that we get by applying Kirchhoff's loop rule to the circuit. And so we need a little bit of calculus to do that. It's not hard. I'm going to do that in another video. I think that's best saved for video number 3. Hopefully this has been helpful, and I'll get to that as soon as possible. Thanks for watching.